Hey everyone, welcome to the next video from chapter 7. So in this video we're going more into theory, unfortunately, and we'll see sort of the idea of having good solutions for linear systems of ODEs, and what I mean by different solutions in the sense of the Wronskian we had before, right? Because the idea before was that the Wronskian told us if the solutions we generated were good enough to meet every initial condition. So we're going to do the same idea here. It's going to require a little more setup, but it's going to be the same sort of process as it was in chapter 3. Let's go ahead and just start talking about it. So we're looking at a linear system here, which, as we've done in the last couple of videos, I know I can write in this sort of form, where it's a of t times x plus g equals my x prime. Now, what we're going to start with here is we're going to start with a homogeneous system. So we drop the g term. So I just have x prime equals a times x. I'm going to drop the of t, but we'll know at this point it's still supposed to be a function of t. Now, for notational purposes, I'm going to use x vector with an upper index here to denote different solutions. So x11 is going to be a set of functions x11 of t through x1n of t. And similarly for x2 up through xn. Because the idea is here, right, when I do solving this problem, I have to specify n initial conditions. So I want to sort of figure out if I get n solutions that solve it, can I meet every initial condition? The same thing with the Wronskian from before, because if I had a second order ODE, like an equation, and to do that I have to specify two initial conditions. Well, if I can find two good enough solutions where the Wronskian is non-zero, then I can meet every initial condition that I want. And so the idea here is the same sort of process. We want to know if I can find n solutions to my system, how do I know if I can meet every initial condition? So if I have x1 through xn as different solutions to my ODE, can I pick c1, c2, cn so that c1 x1 plus cn xn meets any initial condition, like our stuff from section chapter 3. So I need a couple things to start with. The first thing I needed to do something like this was the idea of superposition. And this said I could do these linear combination type things like I'm writing above. So if x1 prime equals a times x1 and x2 prime equals a times x2, then c1 x1 plus c2 x2 prime equals a times c1 x1 plus c2 x2. And now you prove this in sort of a similar way to what we did in chapter 3 we did this. Basically you just use the fact that derivatives are linear, and then you can use the fact that I have these two equations up here, that x1 prime is this and x2 prime is this, just to get me right to the right hand side. So I'm not going to prove it, but this just means that if I have two solutions, any linear combination in this form will also be a solution. So if I have n solutions, any linear combination of that form will be a solution. Now the idea is, can I meet whatever initial condition that I want? So for second order, we had the Wronskian that did this. Right, we had our Wronskian. We'll talk more about that in the next video. But now say we have x1 up through xn solutions to x prime equals a times x. Now what I want to do is I want to stack these guys into a matrix. Stack these solutions into a matrix. And I'm going to call it capital X of t, which is going to be written as x1 in the first column, x2 in the second column, and xn in the last column. If we want to write out all the entries, is going to be x1 function 1 down through x1 function n, 2 function 1, x2 function n, xn function 1, xn function n. So I stack that into a matrix, and then we call the Wronskian of x1 up through xn to be the determinant of this matrix X of T. This looks pretty nasty, and it is hard to compute and everything, but we just define that to be the Wronskian. And then, as before, Wronskian not equal to 0 means I can solve to meet any initial condition. All right, so this is all general theory and works for nth order systems. I think I'm going to stop there with this one. And the next video what we're going to do is we're going to do this as an example with a second order system and show how all these things look, and end up seeing that they look identical to what we had for our second order equations for solving for the Wronskian there. So we'll show that, and then we'll use that as our example to sort of motivate the rest of the theory that's in this section. So that's going to be it for this one. The next video should hopefully make this a little bit more clear, as well as go into the rest of the detail about the theory. So thanks for watching this one, and I will see you in the next one.